Welcome to the video on Household Quality Benchmarking and Engineering Specifications. This is Jim Heisey, Senior Lecturer in Mechanical Engineering. Today we'll be talking about the process for determining the design metrics to ensure the success of your design against a market or competition, and show how the engineering specification sheet works with a QFD to link the design with the voice of the customer. As with the last video on benchmarking, some key terms we want to be focused on today are benchmark, metric, engineering spec or specification, voice of the customer, and shall versus should, or otherwise, as is referred to in this video, need versus want. Now in the DMADVR toolbox, again, there are a number of tools or worksheets that are available in the Excel workbook to help with managing a project. And again, the two sheets that we're focused on are mainly the customer requirements and the engineering specifications. Also included in this video is some views of the QFD and how the information would be put into that worksheet. Looking at engineering specifications, we have to go from benchmarking to design. We have to set metrics. So the first thing is with the market research, looking at benchmarking. What quantifiable metrics have emerged out of there? Were we able to differentiate the needs versus the wants? Are there any attribute metrics that are going to emerge? And were any market leaders defined out of that? From there, we want to set the metrics. So we're going to come up with a list of engineering specifications or otherwise defined metrics that will measure the performance of our system or product and guarantee success in the marketplace. This information that is collected then will go into the respective QFD sections, which we'll show later in the video. So our key focus here is trying to confirm the performance of our product using the QFD. And the main reason we would want to use the Quality Functional Deployment Worksheet is it allows us to show very clearly the connection between the customers, their needs and wants, the product functions and features, the competition or the market as it is assessed and its ability to meet those needs and wants of the customer, and then the subsequent values or metrics that we were able to define for the performance of those competitive products, and later on our own concepts in relationship to the functions and features. So in defining engineering specifications, we're going to get our information first from the project charter from the section of expectations and deliverables. There are project metrics listed there. But we'll also get other values from our benchmarking that we identified on the customer requirements worksheet. And we'll be getting those values or metrics either through published data, through testing of competitive product or processes, or through a practice otherwise referred to as a reverse engineering. Now, reverse engineering is taking competitive product and either through actual contact with the product or through documentation, going through and making an estimate as to what functions and features and components are there in the product and doing the best estimate as to how that product might perform or how it might cost, how it might go together. This is a very common practice in product design engineering. The goal here, though, is to define the performance required for success. So we want to know what functions and features are going to be required for our product or process to be competitive or to fulfill the needs and wants of the customer. We also have to understand what those measures are of the function and feature performance that are needed in order to guarantee success. And lastly, we have to understand what conflicts exist in the design between the functions and features so we know which areas to work on optimization. Key thing is looking at the functionality and features is understanding how many of them do we have to deal with. The ideal state of any product or design is to have the minimum number of function and features that will fulfill the needs and the wants of the customer. Again, because minimizing this count will result in less parts, which will result in less costs and higher reliability of the product or process. So if we take a look at the house of quality, we had these sections that we focused on with benchmarking, the customers, the customer requirements, the market, and how they met the requirements, and then out of that information defining product features and functions. Now with engineering specifications, we're going to focus on the measures section of the QFD and how that information can be applied to the success of our product. We're also, out of this, going to define customer satisfaction goals by looking at the market assessments, and we're going to come up with our own design goals and the design of a product. If we take a look at our own QFD spreadsheet in the DMADVR toolbox, you can see we've got the rankings here, and we have the performance measures that we're wanting to fill out at this time. We also, though, from the benchmark data, will come up with a set of performance measures. We'll be defining the best out of that based against the rankings so that we have a good list of specifications to design against. So some advice about engineering specifications. First and foremost, try to keep them to a minimum. All the must-have metrics or the needs will need to be confirmed, either by analysis or testing or both. Like to have metrics, or otherwise wants, are opportunities for competitiveness and innovation. They are the things that are going to make the customer extra happy if they have them there. However, be careful. Again, getting too much in there will create complexities in the design and verification of the product. Key thing here is to prioritize the impact or the importance. What rises to the top as being most significant for the customer. Again, this is where a Kano analysis can help out. So you want to go out and gather as much information as is practicable by getting either data from competitive product, whether it be published, or getting product and testing it, or getting data from the field, either through service or warranty. If there's no data that can be retrieved on particular items, then reverse engineering may be your best choice, and then the question is whether or not you can yield accurate estimates based on that effort. Important thing here, record your assumptions in the data, because assumptions as they're made may alter or shift as more knowledge comes to bear, and the data is critical to confirm the chances for success. Data is also critical for confirming the rankings that you use and the product's ability to match up against the customer needs and wants. So if we go back and revisit a couple of our projects here, we'll start with looking at the MyerTech cook stove. If you recall from last video, we had these 4 products that we were looking at in order to design a competitive small cook stove for a emerging economy. So we had the benchmarking as was defined here, looking at the customer requirements and ranking of the 4 competitive products and having the market analysis. And moving into the engineering specifications, now the next phase is to come in and again transfer all of the customer needs and wants from the CR worksheet. Again, the reason we do this is we want to keep perfect alignment between what we're developing to what the customer is asking for. If you do not keep this list in front of you, then things can be missed. From there, we'll take a look at, through whatever means possible, and put the competitive information in there for the product that we're looking at. In this case, we have the first of the 4 competitive products listed in here as an example 1. The worksheet as it stands and filled out will have either an option 1, option 2, or a concept 1, concept 2. You can use the same sheet later for putting in the information that you have on each of your concepts if you're wanting to get numbers gathered so that you can do a good job at ranking each of those concepts. This sheet is usable both for doing benchmarking and setting up specifications, or taking your specifications and transferring them over to design concepts as you develop them. So it is possible to have 2 or 3 copies of this worksheet in your workbook by the time you get done with your project. Lastly, as we get the information pulled together on the various competitive products and get metrics defined, then we can start pulling together our list of product specifications. And we have 3 columns in there, though more could be added if needed, in looking at what attributes have to be in the product in order to meet the customer requirements. It's your choice as to whether you list things once or if you list them multiple times as you're trying to link them across with each of the customer requirements. Key thing is, though, documentation, getting everything down so that you have this listed for future reference to either answer questions with management, answer questions in a court of law, or to help somebody who is picking up on this project where a prior team left off, or if somebody's doing history research to do a new product design based on a product family from prior work. Either way, documentation is critical. So if we take a closer look at the information here, we can see the customer requirements that were copied over, and we can see the information that was pulled in for the competitive stove, looking at such things as sales price, materials used, geometry attributes like how thick were the walls, what's the size of the air intake, what was the reduction in fuel used if that information is available, and so on and so forth. You'll notice here too that not in all cases will we have something available, but we may want to list something down so that we have an item that maybe we'll test or go out and continue looking for information. In the case of this particular product, we don't know what the boiling time is on a standard setup with the stove, or we don't know how much time it takes to light the stove to get it burning sufficiently to start doing cooking. But it's okay to go ahead and get those listed in here and either put a TBD or an unknown. Key thing is now you've got information documented in here that either you have or you need to find in some fashion. From there, then we can also, as we get the product put together, again against the list of customer requirements, pull together the product specifications. In this case, after doing research on the 4 different stoves, here's a complete list of different attributes or metrics that would define a complete design that would be competitive in the markets, looking at such things as final assembly cost being $10, have a simple construction process involving no more than 3 hours of labor, and looking at things like the wall insulation and its capability to keep the temperature at or below 55 degrees C maximum during operation, and so forth. You can see here too, as far as items like air intake size and heat channel size or exhaust outlet area, that we have a number of items that are listed as TBD, that is to be determined either through analysis or testing or both as the product gets developed. Key thing is we know these attributes or features have to be included in the design, so they're listed here so we don't overlook them. From there, once we get this information pulled together in our engineering specification sheet, we can now transfer that information to the QFD. Of course, the customer requirements as listed here will go be compiled and put into the sheet. They're already there from our earlier work. We can look at the customer requirements and understand the action terms in there and help us to develop a list of product features and functions which would go into the QFD. After we get that in there, then we can take the benchmark data that we have and list that in there for each of the competitive products, as we can see shown here. Then lastly, as we get the engineering specifications developed, those would go in the goals for engineering specifications. Now you'll notice here that in the case of what we have in the engineering specifications sheet, not everything on that sheet makes it into the QFD. This is okay. The key thing is that we're prioritizing the most important functions and features in the QFD so that we take the most important elements and make sure that they are aligned with the customer needs and wants. If we can do this, our chances of success for the design in the competitive marketplace is very guaranteed. So if we look at aligning the specs with the product features, you'll notice here that when we take a look at the feature or function, then we will see a corresponding value of a competitive product to that function and feature in most cases, and that the values will align accordingly. From there, we can go look across and see each of the different values that we may have, whether it be steps to build, use of materials, or manufactured cost, and we can see the values that would be generated, and then looking at the best of each of these categories, then we can understand the numbers that go in the goals or engineering specifications as being the targets we want to hit to ensure that our product will be competitive. You will also notice that with the rankings that the QFD will give you, that'll give an emphasis on some of the functions and features over others. If we notice here, manufacturing costs is the function or feature of the product that is deemed most important for this market based on the rankings that we have in the meets requirements section. That is listed as 12% of the importance of the tire design, so that would probably be one element in our engineering work that we would focus on very heavily to make sure that we hit our cost targets. Also, you notice that from all those values, we put final specifications together that we're going to hit with our final design, looking at things such as material count, specs to build, and steps to build, and use of materials. We've been able to come up with some values that we believe will be competitive in the marketplace, as well as manufacturing costs and many of the other features that are here. If we take a look at our second example with a Regolith mining competition, again, a reminder of the 4 different designs that we were benchmarking here and their key attributes that we were focused on. And again, the NASA rules as they were established and the points that determine the best aligned design with the NASA mission requirements. From there, as we're developing specifications for this design, we want to ask ourselves what function and features are needed to meet all the requirements and the goals or the metrics for them that NASA has stated. In this, NASA refers to it as a requirement flow down, that is understanding the main overall system requirements and then determining how those values flow down into the subsystems and components of the major system being developed. So we want to ask ourselves what values become evident for the function and features in order to meet the mission requirements and be acceptable or competitive. Also, are all the goals quantifiable, or do attributes exist that have to be tracked? From there, can some of the function and features be combined so that we can simplify the design, making it more reliable? So again, we had our benchmarking with a number of values put in here for each of the product. If we take a look at our engineering specification worksheet, we'll see once again that we copied over the customer needs and wants, which in this case are reflecting the rules requirements from the competition. Then we also get as many values put in there on the various different products that we benchmarked, or in this case the rovers, and got a number of values in there that we were able to either get directly from data from NASA or by doing some reverse engineering by looking carefully at the pictures, taking scale measurements or counts, and applying that information here. Lastly, once compiling all the benchmark data, then we're able to come up with a list of product engineering specifications for our new rover design that would guarantee competitiveness. Once again, in this design you can see that there are a number of values that haven't been set yet. They need to be developed as the design proceeds. So if we take a closer look at that, our needs and wants again, such as collecting maximum amount of material in 10 minutes time, but making sure that we have at least 10 kilograms so we get points. Reducing the number of sorties required in 10 minutes time, maximizing the number of sorties per 10 minutes without tip over, minimizing the energy use in digging, making sure that the rover is light, make sure that we don't generate too much dust during the mining, and make sure that the design is durable, has good traction, and is reliable. We take a look at the values on some of those rovers that were investigated. Here for the West Virginia, we can see that it had an average collection rate of 14.3 kilograms, that it was utilizing one large scoop that had volume of 28 liters, that its hopper capacity was approximately 100 kilograms, that it would typically dig about 5 centimeters deep. It would use 3 sorties during the 10 minutes competition to complete its mission. and that its typical scoop speed per minute was 2 cycles per minute. Lastly, now the rover weight was determined to be 58 kilograms, and that there was no dust mitigation features on the rover. As you can see, some of this is quantifiable. The dust mitigation is an attribute, but we can still make enough assessment on a good design even with the attribute. If we take a closer look then at the specifications that were generated, you can see here that we're coming up with a target for scoop volume and the number of scoops, and the belt speed needs to be determined. This would be a case of balancing forward speed with conveyor speed in order to not overload or underload the scoops and thereby maximize the efficiency of the mining rover. We're seeing that in order to be competitive, that we possibly want to have a hopper capacity that's slightly larger than it was before, and that we're looking at targets for traversing speed or digging speed based on the math that was pulled together. Key thing is, you notice that the TBDs, and there are a number of them in here, are going to be design variables that will be adjusted in order to meet the other objectives, such as the average mining rate, which in this case was determined to be 16 to 20 kilograms per minute. In order to do this, a model of the mission run would have to be pulled together in order to ascertain what sort of traversing speeds and mining speeds would be necessary in order to get the required number of runs in the required time, which in this case is 10 minutes max. So if we take a look at the QFD related to the space mining rover, we can see the information that has been put in here from our benchmarking analysis. In this case, you can see that we've got scoop system volume set up. The units will be listed on the DMADVR toolbox for each of these. In the case of the scoop system volume, the units there are going to be liters. The hopper volume is also listed in liters. Excavation drive speed is going to be listed in cycles per minute. Excavator drive force is going to be in newtons. Track speed, meters per second, and so forth. You can look at the DMADVR toolbox examples to see the complete list of information, as well as other attributes such as the trade-off area, looking at how each of the features relate to each other, whether they're complementary or in conflict. Another item I want to point out here is that you can see the decision matrix in there and the values that each of these systems has. So lastly, with engineering specifications, we can see the DMADVR toolbox customer requirements and engineering specification forms will help us collect the customer requirements, will aid us in developing good, clear engineering specifications. And that putting this information into the QFD then allows us for a quick visual connection between what the customer was asking for and how the design will deliver on that promise to the customer. Lastly, perform functional decomposition to help us identify the functions and features and how those systems would perform. Next step after this, be making final design decisions and coming up with a clear concept winner to move forward into the development phase of our project. This completes the video for engineering specifications. Thank you for watching.